Hello everyone, welcome to the channel Learn Math with the Shobita. Today I am taking a lecture on group theory. I have already taken one session, so continuation of that. In the last session I have given the definition of group and some examples. So now in this today's video some more examples of groups. Let us see what are they. First example, the set of integers under ordinary multiplication is not a group. It is because the inverse element does not exist. If a is an integer, then 1 by a is not an integer. 1 by a is the inverse of a, but 1 by a is not an integer. So set of integers under ordinary multiplication is not a group. In the last class, we have noted set of integers under addition is a group. 0 is the identity element that exists and minus a is the inverse. Okay. Next, the set of natural numbers. The set of natural numbers starts from 1 to starts from 1. It does not include 0. So it is not a group with respect to addition as well as subtraction and multiplication, because the identity element 0 does not belongs to n. Also for multiplication, the inverse element does not exist, and the subtraction is not closed for set of natural numbers. If we subtract any two numbers, for example 1 minus 2 minus 1 does not belongs to n. So the n is not closed under subtraction. Next example, the subset 1 minus 1 I minus I of set of these four elements of complex numbers is a group under the complex multiplication. Here identity element is 1 and inverse of 1 is 1 itself, inverse of minus 1 is minus 1 itself, and inverse of I is minus I, inverse of minus I is I. Okay, so this is a group. Next, the set of q plus of positive rationals is a group under ordinary multiplication. The inverse of a is 1 by a. Identity element 1 exists. Next, the set S of positive irrationals together with 1 under multiplication satisfies the three properties given in the definition of a group. That is, it is closed under multiplication, associative law, as well as the it is not closed. It is satisfies the associative property, inverse exists, as well as identity element 1 exists, but it is not a group because it is not closed. If you take any two rational, say root 2 into root 2, it is equal to 2, but 2 is irrational, so it does not belongs to the set of irrational numbers. Okay. Next example, the set of all 2 by 2 matrices with real entries is a group under component wise addition. Here the 0 0 0 is the identity element, minus a minus b minus c minus d is the inverse of a b c d. It is operation is addition operation, component wise addition. So in general, n by n matrices, set of all n by n matrices is with real entries, complex entries are all group under the operation matrix addition. Okay. Next example, the set Zn starts from 0, 1, 2 to n minus 1 for n greater than or equal to 1 is a group under addition modulo n. For any j greater than 0 in Jn, inverse of j is n minus j. This group is referred to as the group of integers modulo n. Okay. If g equal to, it is if g equal to 1, 2, 3 n minus m minus 1, then g with respect to addition modulo m is not a group because here 0 does not belongs to g. Okay, so for Zn, if it starts from 0 to n minus 1, then it is a group under addition modulo n. If it starts from 1 to m minus 1, then it is not a group for addition of modulo m. 0 does not belongs to this. Okay, I am explaining all these examples because one of the question, which of the following is a group, which of the following is not a group, is the one of the most expected question in the KCET examination. In KCET 2023 as well as in KCET 2024, they have asked which one of the following is a group. Such a question is asked. For that purpose, I am describing all these things. Next example, the set of set R star of non-zero real numbers is a group under ordinary multiplication. The identity element is 1. The inverse of A is 1 by A exists in R star. Further, the group is this is a group. Further, what would be an abelian group? A group is said to be abelian if AB equal to BA for all AB belongs to G. Okay. Here for ordinary multiplication, the set R star of non-zero real numbers is an abelian group. Okay. Next, the set of all 2 by 2 matrices with real entries and non-zero determinant is non-abelian group under the matrix multiplication operation. Not as 2 by 2 matrices, all n by n matrices with real entries, non-zero determinant is a non-abelian group. Okay. The identity element is the identity matrix, that is 1 0 0 1, and since the determinant is non-zero, inverse exists. This group is called general linear group of 2 by 2 matrices over R. Next, the set of all 2 by 2 matrices is not a group with respect to matrix multiplication. Set of all 2 by 2 matrices. Okay. Here, set of all 2 by 2 matrices with the non-zero determinant is a group, and set of all 2 by 2 matrices is not a group with respect to matrix multiplication because the inverse does not exist when determinant is 0. Okay. So out of the set of all matrices, if we consider the matrices with non-zero determinant, then that set is a group. If we consider all the matrices, then it is not a group with respect to matrix multiplication. Remember the point. Next, let un denotes the set of all positive integers less than n and relatively prime to n. Then u of n is a group under multiplication modulo n. If n is a prime, then u of n equal to 1, 2 and so on n minus 1. This is a group under multiplication modulo n if and only if n is a prime. So that is the next statement. The set 1, 2, 3 and so on n minus 1 is a group under multiplication modulo n if and only if n is a prime. This is the important thing. Next example, the set of integers under subtraction is not a group since the operation is not associative. Okay, if we take any 3 elements, say subtraction operation is not associative. Okay, you can check. Next, the set of complex roots of unity cos k into 360 degree by n plus I sin k 360 degree by n, k from 0 to n minus 1 for all integers n greater than or equal to 1 is a group under multiplication operation for integers greater than or equal to 1 is a group under multiplication. Next, one of the sample question, most probably asked question in KCET examinations. First, which of the following sets are groups under usual addition operation in numbers? Set of even integers, set of all z is zo, set of all odd integers, then set of all a by b such that a comma b belongs to set of integers b is odd. So which one is the group? Let us check. Set of all even integers, clearly it is a group under addition operation because addition of any two even number is an even number. Also the addition is operation is associative. Further, 0 element belongs to set of even integers, so 0 identity element exists, and minus a is the inverse element also exists. Next, set of all odd integers. Set of all odd integers is not a group because identity element does not belongs to the ZO, as well as the addition of any two odd integers is an even integer. So it is not closed under addition operation. Okay, set of all odd integers. Further, under addition operation, the set a by b, a comma b belongs to z, b is odd, is a group. Why? The operation is associative, clearly it is closed, and the identity element 0 equal to 0 by 1 is the identity element, and minus a by b is the inverse element. Since b is odd, here minus b is also odd. So all the properties is satisfied this set, hence it is a group under operation addition. Next question, which of the following sets of numbers are groups under multiplication operation? It is set of non-zero integers, set of non-zero real numbers, set of all a by b where a comma b odd integers, both a and b are odd integers, and set of all of the form a plus b root 2, ab belongs to q with a not equal to 0 or b not equal to 0. Okay, and set of non-zero integers is not a group under multiplication operation. I have already told, because inverse does not belongs to the set of integers. And our set of non-zero real numbers is a group under multiplication operation. It is a abelian group. We know that. Next, let us check whether the set a by b is a comma b odd integers is a group with respect to multiplication operation. It is a group or not. Okay, so let us take any two elements. Then if you multiply, I will get this is an element of S, because product of odd integers is an odd integer. Further, the clearly associative law holds. Further, the identity element 1 by 1. Since 1 is an odd, this belongs to the S, therefore identity element exists. Next, for any a by b belongs to S, b by a is the inverse element. Clearly, they have given a comma b, a and b are odd, so b by a belongs to S. Hence, identity element, inverse element, and associative closure law, all the properties are satisfied. Therefore, this set is a group under multiplication operation. Suppose the set is given like this: a by b, a comma b are integers and b, only b is odd. If a is not odd, then this set is not a group under multiplication operation, because the inverse element b by a, where a may be even, so inverse element does not exist. Therefore, this set is not a group under multiplication operation. Next, let g equal to a plus b root 2. A, b are rationals with a not equal to 0 or b not equal to 0. Clearly, the commutative law, closure property holds. Also, associative law holds. The identity element 1 can be written as 1 plus 0 into root 2 belongs to G is the identity element. Further, the inverse 1 by a plus b root 2, rationalizing the term, I got this as a by, here I am rationalizing into 1 a minus b root 2 divided by a minus b root 2. So I got this as, and clearly a square minus 2b square not equal to 0. Suppose a square minus 2b square equal to 0, then we get a by b equal to root 2, which is a contradiction because root 2 is irrational. So clearly a square minus 2b square is not equal to 0, and this belongs to the set G of the form a plus b root 2. This is belongs to set of rational numbers. This is also rational. Therefore, G is a group under multiplication operation. If you want, please pause the video and analyze the calculation. Next, consider the set of all 3 by 3 matrices with real entries of the form 1AB, 01C, 001. Let us verify that this is a group under matrix multiplication. Okay. Sometime they may ask whether this is a group or not with the four options. So let us check whether this is a group or not. Say the calculation I have done. It is closed under matrix multiplication. So if capital A belongs to G, capital B belongs to G, then A into B belongs to G. Clearly, first property is satisfied. Next, matrix multiplication is associative. Also, the identity matrix is the identity element. Further, let us evaluate the inverse element. So I have made the calculation. If you want, please pause the video and see the calculation. I will not explain all those things, elementary calculation. So after calculating, I got the inverse element as 1 minus A, AC minus B, 0, 1 minus C, 0, 0, 1. That is, the inverse element for this is 1 minus A, AC minus B, 0, 1 minus C, 0, 0, 1. This is the inverse element. Clearly, this is of the form 1AB, 01C, 001. So clearly this belongs to that set. Therefore, this is a group for the multiplication operation. Therefore, G is a group with respect to matrix multiplication operation. Further, it is not an abelian group. I have not calculated this. Please check yourself. Otherwise, the video will be too lengthy. Next, another example. Let G is the set of all 2 by 2 matrices of the form A, where A is a real number and A not equal to 0. Then G is an abelian group under matrix multiplication. This I have solved in the last video. I have solved it for n by n matrices. Okay. Here the identity element is 1 by 2, 1 by 2, 1 by 2, 1 by 2. Clearly this belongs to the set G because 1 by 2 not equal to 0. And the inverse element is 1 by 4a, 1 by 4a, 1 by 4a, 1 by 4a. Clearly this belongs to the set G because a is not equal to 0. So this is an abelian group under matrix multiplication. Okay. Next I will make two remarks. If G equal to 0, 1, 2 and so on p minus 1, then the group G with respect to multiplication modulo operation is not a group because the inverse of 0 does not exist. Okay. If G equal to 1, 2, 3 and so on p minus 1, and if p is not a prime but composite integer, then also G with respect to multiplication modulo operation is not a group. Remember these 2 points. Okay. Also, if the elements of non-singular matrices are integers, then G is not a group, since inverse of every element does not belongs to G. That is, if G is the set of all n by n matrices like this, and if the elements with the determinant is not equal to 0 and the elements are integers, suppose these elements are integers, integer entries, then such type of set is not a group because inverse of a element does not exist. Inverse may include some numbers like 1 by a, 1 by e. Clearly 1 by a, 1 by e is not an integer. So such a set of non-singular matrices with integer entries is not a group. Thank you friends. Please share and subscribe the channel. If you have any doubt, ask in the comment section.